I'm Corrado Monti. I'm presenting this work done with Paolo Boldi and Irene Cremaldi. We are talking about a network model with latent features on its nodes. So a complex network that has features on its nodes. We can look at many examples in reality, like a co-authorship network where the features can be the interest of each author. Another example can be a semantic network, so semantic relationship between concepts. And in this case, features can be the categories of each concept. So there are a lot of examples in reality of a complex network structure in this way. What we want to do is to obtain a model that describes such a network. What behavior do we want from such a model? Well, the most obvious one is homophily. So birds of a feather flock together. Nodes with similar features tend to form links. But we can think of less obvious examples, like, Uma Thurman is an actress, and Quentin Tarantino is a director. Well, these two categories, these two features are different, but they tend to form a link between each other. Another example is Montague and Capulet, the rival families from Romeo and Juliet. Remember them? Well, if the point of the work of Shakespeare is that if your feature is being a Montague and the other node feature is being a Capulet, it's very, very hard to form a link between you two. So this talk is going to be structured in two parts. The first part is about getting a model for the association between nodes and features, and the second part is how to get from these features to a network. So this is just a slide about the notation, but whatever. So first part, how can we model the association between nodes and features? Well, we're going to use a model that is the India buffet, that is quite well known, but I'm going to recap it a bit. Presented in 2005, and the metaphor is the following. We think of an Indian buffet restaurant where customers are our nodes, and they have to select a set of dishes that are our features. So how does it work? The nth customer arrives, and it selects a number of new dishes that weren't tried by anybody. This number is distributed according to a Poisson distribution regulated by parameters alpha and beta. And apart from these new dishes, it also selects a number of dishes already tried by others. So where the probability of tasting a dish depends on the dish popularity. How did we change this model? Well, the consideration that we did is that in reality happens often that different nodes have a different ability to influence others. So again, we can think of many examples here, and sometimes this is good, sometimes this is bad, but in reality, there is a different fitness across different nodes to transmit their features. So how did we model this? Well, we considered that the probability to get the k features is the sum of the fitness of all other nodes that tried that feature before. In this way, we got the result of the most popular feature gets chosen more often, so we get a richer effect, and also there is a competition, so it depends on who got it before. Now, back to the parameters of the Indian buffet. They are very clearly defined, and they have different roles. In particular, alpha regulates the number of total features that have been introduced, while beta regulates how these features are distributed. So basically, the asymptotic power law behavior in the long end. And we have unbiased estimators for that, for both these parameters, and we'll see later how can we use them. But to fit them on a slide, I'm assuming that the expected value of the fitness of each node is 1, and in this way they can be estimated with this pretty nice formula that are short and concise. So here we are assuming that we know a real node feature association, so we know the vector of features for each node. And we can get back to alpha and beta that generated this real node feature association. Now that we have estimated alpha and beta, how can we go back to the fitness parameters of each node? Well, now we have a probability for the node feature association that we are looking at that depends on the fitness parameters. So we can look at this as a likelihood, the likelihood of the fitness parameters given the real node feature association that we have. So we can use a Gibbs sampling technique to maximize this likelihood and go back to the fitness parameters that generated those. So we did some numerical experiments with this, assuming that the fitness of each node is distributed according to a discrete power law. And the results we got are summarized in this plot. We can see from the plot on the left that it depends very much on the order of the node that we're considering. For the first nodes, we have a lot of information. They influence all the others. While for the last nodes, they influence basically nobody. So it's very difficult to get some sense of if their ability is high or low. But however, for the first square root of nodes, so the square root of n nodes, we get a kind of tau. So we are measuring how correlated is the rank of these two, of the original order of nodes by fitness and the order that we found. So for the first square root of n nodes, we got a kind of tau of 0.73. For the first half, it goes down, and considering all the nodes, it goes to 0.3. So how can this model be used? Well, let's look at this data set. They are scientific papers, and it's a citation. And these are scientific papers. They are ordered by publication date, and the features we considered are words, scientific words from the abstract of each paper. We put one if the paper has this word, and we get this node feature association represented here. From this, we can estimate the models according to the way that I've shown you before, and we can get back to alpha and beta, use adjust the sparsity of the model that we're going to generate, and use them to generate a new matrix. And this is the results we got. This is interesting, I think, because we can look at this as a node feature association that is different from the original one, but is drawn from the same distribution. This can be useful in other ways that we are currently looking into. Now, second part, how can we get from such a node feature association to a network? So the first ingredient of this is a feature influence matrix that we will call Xi. In this matrix, so the element Xi hk corresponds to feature h linking to feature k. If the value of Xi hk is positive, then it will foster the links from the feature h to feature k. If it's negative, it will discourage those links. And obviously, the absolute value of this number determines the magnitude of this effect. So please note that this can model all the behavior that we discussed in the beginning. And in particular, if we're assuming the identity, then we get the simple homophily behavior that I presented before. And we will look at this in the experiment. So then, apart from this matrix, we need an activation function called phi. And what is the role of this is to get from a number to a probability, and where the number is the one in the formula. So basically, we are taking all the elements in the feature matrix that corresponds to the feature that we are seeing in a couple of nodes. So all the feature of the first node, all the feature of the second node, and we sum all the elements of the matrix corresponding to these features. So basically what happens here is that the matrix C acts like a kernel in the outer product of these two binary vectors, and it then gets translated by the activation function into a probability. Now, this activation function in practice will be a sigmoid with a parameter theta and k, where theta is the center of of the sigmoid, while k determines the smoothness, so how rapidly it goes from 0 to 1. And please note that for k to infinite, we get a step function, so a deterministic model. This will be useful later. The fact that we have those parameters is nice because we can adjust those parameters given a wanted density for the graph. So if we want a graph with a given density, a given number of edges, then we can solve numerically this equation and get the parameters of the sigmoid in order to get the wanted density. This is what we did in practice, and this is an example. So we have a citation graph between papers, and we can see here the degree distribution in this graph that resembles a power law, and under it the distance distribution shown here in a cumulative form, highlighting the peak value, so the percentage of reachable pairs. We use the same matrix that I've seen before and an influence matrix corresponding to the identity. And to make our simulation, and we set the number of arcs to correspond to the original graph. In this way, we can determine the parameters of phi, particularly in theta. And this is the results we got. So there is a very clear power law in the degree distribution, while that is a pretty local property, while the global properties of this graph is very realistic. It resembles closely the one of the original graph. This changes very much if we change k, the parameters of the sigmoid that regulate the smoothness. And in particular, we can see that the connectivity, the number of reachable pairs goes down as k goes up. This is an effect of the fact that here we are considering the identity matrix as an influence matrix. However, we can see also that the power law of the degree distribution is more and more close to a power law while k goes up. In particular, for k to infinity, so its step function is very clear power law. Okay, this is the fact that we're using an identity matrix as an influence matrix has some consequence, but how can we get a realistic feature-feature matrix? So we're going to simplify the model a bit. And in particular, we are going to assume that k is infinite. So we have a step function, as I said before, and the model gets deterministic. And we're going to use, as a threshold, we are going to use 0. So basically, this simplifies the model in the way that if the sum of all the right elements in the matrix is positive, then we get a link. If it's not, we don't. Okay, why is this useful? Well, because this is equivalent to the prediction rule of a perceptron if we apply an outer product, a kernel that is the outer product kernel. And what does it mean? That if we represent the two nodes as binary vectors, and we feed to a perceptron, so a very simple neural network, this couple of nodes, then we make it learn if these two nodes are linked or not. So we ask it to predict 1 if this couple is a link and -1 if it's not. Well, what happens is that the internal state of the perceptron corresponds exactly to the latent feature matrix that we are looking at. A pro of this method is that it's actually very efficient. In particular, we tested it on Wikipedia. And Wikipedia with its hundreds of millions of links, and it takes like 9 minutes to run on all this. So we're going to. There is no time to show you all the empirical evidence that we got on that, but I can show you a nice anecdotal example of this. We're going to look at this latent matrix that we found, assuming it is a graph. So we are looking at a graph that is the latent feature graph that is behind the graph of the nodes, so that explains them. And this is a particular fragment of it around science fiction films. We can see that science fiction films links to dinosaurs. We can see prehistoric reptiles under there. We can see the space flight above. And we can see that science fiction novels links to science fiction films. And as a science fiction fan, I'm pretty satisfied with this, and I can conclude my talk with it. Thank you very much, and I'm glad to take questions.
Thanks a lot. We've got plenty of time for questions. I guess that the coffee break is...
Yeah, I'm glad to take questions in a coffee break.
Okay.
More than.